state C and the output bits are 1, 1, 1. Okay? Now you are in state C, you can go to state D. D is 1, 1. Okay? And it produces 1, 1, 0. Okay? If you are in D, you can go back to D again. And the output is 1, 0, 1. Okay? From D, you can reach state B. State B, well, of course, these boxes, the color is irrelevant. B is 0, 1, and the outputs are 0, 1, 0. And if you are in B, you can reach A. If you are in B, you can reach A. You can reach A, and the corresponding bits are 0, B2, 0, 1, 0, 1. Okay, and if you are in state C, if you are in B, you can also reach. You can also reach C. State B to C. We haven't drawn that, is it? B to C. B to C. We didn't draw it. Okay. B to C, and the branches are 1, 0, 0. B to C, 1, 0, 0, and from C you can also go back to B, 0, 1, 1. Is it 0, 0? Okay. Well, this is a table you maintain anyway when you implement the method algorithm or the math decoding algorithm, right? You have to maintain this. Okay? State diagram. This is the state diagram. Okay? See, the reason why we are doing this is that we want to obtain the distance properties of the convolutional codes from this state diagram. You can get it. I will show you how to get it. Once you know the distance properties, you can get the union bound of the probability of error for maximum decoding using distance property. Both the sequence error rate and pairwise error probability as well as bit error probability. Okay, we'll show. Okay. So now what we will do is we will re-represent this state diagram in a slightly different fashion. Okay. Where in A Okay, and you can reach C, A to C. Okay, so what we will do is that the convolution code is linear. If there is an all zero path, okay, if there is a linear path that is diverging and remerging, okay, and these ones give you the number of ones in this path of first error event gives you the minimum distance, right? In the first error event, the number of ones give you the minimum distance because that is the Hamming distance of this path. Okay, so since the code is linear, you don't have to take the all zero sequence. You can take any two sequences, still you will get the same minimum distance. Okay, you don't have to take this as the reference. You can take any path as the reference. Okay, and if you compute the first, if you figure out the first error event, okay, between two any valid code words, you should get the same minimum distance. Okay, but without loss of generality, we will take the all zero path as a reference. Okay. Okay. Now we'll create a label for this branch as d raised to 3, where 3 is the number of ones in the coded bit, because the all zero path is a reference. So you count the number of ones, and the exponent is the Hamming distance on this branch. Okay, from A to C. From A to C. Okay, we'll see why we are going to do that. But from C you can go to B. Okay, from C you can go to B. C to B, and the Hamming weight is e raised to 1. Okay. From B, you can also go to C, and Hamming weight is in this other direction. Huh? E raised to 1. Okay. And then there is this D. D. From B to D, the weight is again not B to D, it's D to B. It's then in D, you can go from D to D, and the weight is D square. In A, you can go from A to A, but the weight is 0, so we'll eliminate it. That doesn't contribute to the Hamming distance, so we don't include it. We can put a circle here, D rate 0, so it doesn't contribute any weight. Okay. From D to C, or C to D rather, C to D, it is D square. Okay, and then B to A, it is D square. B to A, it is D square, and we'll split this. It is the beginning and it is the end. I'll call it E instead of A. That is the end. Okay. So these nodes, this represents the input. and this represents the output for this state diagram. Okay. Of course, you can connect it. Okay. This is split into two nodes. A is split into two nodes. Now let's look at the input-output relationship. Okay. Here, xc is equal to dq into xa. Okay, this arrow. Now how many arrows are coming? Xc is equal to d cube into xa plus xb into d into xb. We're trying to get the transfer function from between input and output. Okay. And xb is equal to, let's see, xc into d into xc plus d into xd. Similarly, xd is equal to d square into xc. We are basically looking at inward arrows plus there is a self loop, then d square into xd. And finally, xe is equal to d square into xp. Okay, and the transfer function t of d is equal to xe by xa, output by input. And that turns out to be, if you work out, d raised to 6 by 1 minus 2d square. And if you expand it, you will get d raised to 6 plus 2 into d raised to 8 plus 4 into d raised to 10 and so on and so forth. That is equal to ad d raised to d. D is equal to d free to infinity. AD are the weights 1, 2, 4, and so on. Well, it's not. AD is equal to 2 raised to d minus 6 by 2 for d even and is equal to 0 d odd. Okay. So in this code, the first element, okay, the exponent 6 is the free distance, free Hamilton distance. Okay, and there is only one path that contributes to this Hamilton distance. That path is 1. Of length 1, means number of paths is 1. So what is that path? A, C, B, A. What is the Hamilton distance? 3, 4, 6. And how many such paths are there? The first error event, there is only one path that gives you the first error event. Okay? In the second term in the exponent, there is another, this is the second error event. Okay? That has Hamming weight 8, and there are two paths contributing to that. Okay? Let us see. 3, 5, 6. Well, let's see which one is the 6, 7, 8. It is A, C, D, B, A that has Hamming weight 8. And there are two. There might be two such paths. Okay, let me see. Well, we have to complete this trellis. You will find yet another path. Okay. complete that release, you will find it. Let me see what would that other plus one. Huh?
3, 1, 1, again, 1, AC, BC,
AC, DBE, and the other one is A,
AC, BC,
AC,
BC.
BCB. A, C, B, C, and then
DA.
okay. From C to B, what is the weight? Huh? What is the code sequence? C to 001, and then the last one is 011. You can count it. Okay, this should also have 8, and there are 2 such paths giving you having distance. So this gives you the distance factor, and you later on you will see this path multiplicity is also important because in the union bound you have to also take into account how many paths contributed. Okay, if there are 2 paths, then error events will, the probability of error will increase. Okay, but luckily in this case there is only the first error event has a path multiplicity of 1. Okay, this is called the distance spectrum of the convolution. Now we will generalize it further. Okay, and you will see why we need. In order to compute the bit error probability, you also have to know this is all 0 path and this is the first error event. You also want to know how many ones are there in this path. Source ones in the sense corresponding to source bits. This is a 1, 0, 0, 0. So the source would produce 1 error. Okay? So that is also important to calculate the bit error probability. In the first error event, of course, first error event by definition there is only one source bit. Okay? So now we will generalize this a little further. Okay? Okay, now we will introduce a factor n into all the branch transition caused by the input bit 1. Okay. Let us see. First, let's identify the. This is caused by input bit 1, A to C. A to C is caused by this color, right? So I'll first color them, okay? And this is also caused by 1. This is caused by 1. This is caused by 1. And the rest are caused by 0. Okay? You have to carefully do this, okay? Okay, now, since this is caused by a 1, I'll just put a factor m in front of this, and every time the cumulative exponent on n increases by 1, only if the branch transition is due to an input 1. Okay? Okay, so there is an n there. Then there is no, this is caused by 0, so we won't put an n here. This is caused by 1, so we'll put an n here. Okay, you'll see the effect of it. Here there is an n. Here there is an n. That's all, right? So whenever the transition is caused by the 1, we put an M there. Okay, we'll see what happens by having this 1. Okay. Okay. Then we'll do one more thing. Okay. We'll also introduce this factor J. Okay. This factor J will serve as a counting variable to indicate the number of branches in any given path from node A to node E. Well, there is only one branch, so well in this case there is only one. Number of branches from here to here is 1, so it's obvious, right? So everywhere you put a J in this particular. Okay. Now what we will do is we'll now modify this equation J and D cube, J and D, JD XC, JD, JN, JN, J. Okay. J cube then divided by 1 minus J and D square into 1 plus J. Okay, that is a transfer function. Now it's a function of J, N, comma, D. Okay. This turns out to be J cube N D raised to 6 plus J raised to 4 N square D raised to 8 and so on. It's a big series. Okay. Okay. Let's take the first one. The Hamming distance is 6. That's what it indicates. There are 3 branches, 1, 2, 3. The length of this first irrelevant path is 3. It's composed of 3 branches. So this gives you 3. And n raised to 1 indicates there is a single error in the source. Okay? Let's take a look at the second one. J raised to 4 n square d8. Well, second irrelevant by definition is there are 2 errors, 1, 1. Okay? Hamming distance 8 and this is 3 branches, this turns out to be 4 branches. 1, 2, 3, 4. So this transfer function gives you a good picture about the distance spectrum. Okay? One, two. This is all 3. Huh? Huh?
2 parts are there.
The second one will write. Plus j raised to 5, j raised to 5, n square di. The second one is 5. It captures the entire spectrum. Okay. So this transfer function is the nice tool that describes the properties of the code. Okay. Now, this one. If you start here, it won't change. That's what I said. The code is linear. You can take all 0 path and you can draw this trellis and draw the state diagram in this particular state diagram anyway doesn't change. It depends on okay. This state diagram, you'll end up with the same state diagram. Here we start somewhere here, let us say. Okay, and you take not necessarily on all 0 code word. You take any 2 valid paths.
The only thing is defining the Hamming distance. Some difficulty.
No, no difficulty. You just compute Hamming distance. It's the difference between the code words. Yeah. So you just capture it, but in the end, these exponents will remain the same. It's a linear code, so you did not necessarily take all 0 code word as the reference. That's what we do. In this case, okay, so how does it help us in calculating the error probability? Let's go back to the maximal likelihood decoding. Okay, I will not go through the entire derivation. I will just go to the end of the derivation. Remember, the probability of error was the pairwise error probability was derived as AD P2 of D, D is D free to infinity, that is equal to AD, and this is a Q function of square root of 2 EC by N naught into E. This is a pairwise error probability. Okay. So let us say the exponent of n is written as some f of t. F of t is the exponent of n in the distance spectrum. Okay. Then the bit error probability okay. So we'll have to take into account how many bits are in error, right? So in the to calculate the bit error probability, all you have to do is probability of bit error is less than the union bound d equal to d free to infinity. Of course, you know this. Usually the first few terms will dominate. Normally, even sometimes the first term will dominate. In low SNR regime, anyway, union bound is okay. Beta d is in this case AD and exponent of n is fd. What is the role of exponent of n? Well, exponent of n tells you how many errors are there, source bit errors are there. So for the first term, there is only one. For the second element, there are two, and so on and so forth. But normally, you know, this in the ISNR regime, it's only there. In the very ISNR, this is what will dictate the performance, because FD is 1 in this case. Okay? The first element generally dictates the ISNR. This is the highest and okay. So when you design codes, what is the criteria that you want to adopt? Well, you want to maximize D free and you want to minimize the path multiplicity. Right? It's preferable to have a single first error event with a say path multiplicity of 1. Okay. And preferably these are maximized. Anyway, this is anyway greater than 6, but if it is insolvent, if it is 10, it's even better. Then the contribution will be less and less. So if you have a 7, 8, and so on and so forth, then the second error event sometimes starts to contribute to the error problem. So you can actually design a convolutional code into a computer system. For systems with large constraint lines, it's a little difficult to analyze the performance. Because since there are only 4 states, we are able to draw the state diagram and get the transfer function extractable.
So this gives a lower bound in the
It's an upper bound on the error. It's a union.
So we can't have a decoder this can be better than this.
No, this is an upper bound on the actual construct. It's nothing to do with the decode. This is a maximum likelihood decoder. We are calculating the probability of error. We are bounding the probability of error of the maximum likelihood decoder, or decision maximum likelihood decoder, and we have obtained an upper bound. Usually, this is the type. You can simulate it. You can take the code. You can simulate, calculate the minimum distance, calculate the path multiplicity, and at ISNR it should match. Maybe a small difference. You should be able to analytically calculate this and simulate, and they should match at ISNR, or rather a small gap. For the codes we have, we should be able to. For example, that simple code we dealt with, we should be able to calculate the transfer function. Okay. Usually, for convolutional codes, the D free is on the order of 20, 25, and the constraint length is on the order of 6, 7. Broad these are stables. They are given. And you can extend this analysis for non-binary codes, but most applications we use binary convolutional codes. Rate half, rate 1/3 is a very typical codes. Rate 2/3. These are typical kind of codes. Okay. And you say, you will put infinity here, but what if you might say, what if it is a very short code? Then you have to truncate it to find a number of codes. But if it is a very long code word, then you have more terms. But as I said, the contribution of first term is the highest, and subsequent terms is not so. Okay, with this now I think we have established BCG algorithm, and we have a convolutional code. We analyze the distance properties and the maximal likelihood decoding group. So now we are ready to move on to turbo codes and infinity codes. The only thing we haven't covered is block codes and BCG codes. I don't think we have time for that. This semester we stick to convolution codes and turbo codes. We will also see how to achieve capacity. That also, once we build a decoder, we'll see how to characterize the performance of the code and how far it is away from the capacity. Okay, we'll stop here today.
distance here, D3 is the minimum distance.
Yeah, minimum distance. Yes.
Minimum distance. So generally we will calculate with the block codes like we'll take the k bits and take code words like n is the code word length and k is the input length of the block code. Minimum distance is the total 2 power 3 possibilities will be having as a code word.
Right.
The minimum distance between all possibilities will
See,
be
you have code. There are a lot of code words. Right?
C0,
C0, C1, C2, C3.
2 power 6 k.
Yeah, any number. Okay, whatever it is. You take any page. You calculate the distance. Okay. And among all these distances, it is the minimum that dictates the error problem.
Yes, sir.
It's the same here, same notion.
How is it like same notion here? Like here.
See, we took the all zero code word as the base, as we fixed that as the first code. Okay. All zero sequence
means the length of the sequence.
No, convolutional code, they are not
It's not
fixed
block
length.
code.
This is infinite length code. Block codes. I mean, here also, you know, if you have you have n information bits, you have code length of some p or something, you have 2 raised to p possible sequence. Okay, but anyway, there are large number of possible sequences. But we don't care about all that. You take the all zero code words as the reference, and we identify the first error event. Okay, and there is a code word associated with it. Okay, and the distance between the all zero code word and the code word attached to the first error event will give you the minimum distance. Because any other event will have a higher minimum distance. You have seen that. It cannot have lower. Because it has more ones. The longer the code word, it will have more. So block codes analysis is a little different. There, in fact, the minimum distance is always less than or equal to n plus k minus 1 for a k by n code, right?
Minimum distance.
The Hamming distance. There is the singleton bound. Yeah, k plus n minus 1. Maximum achieved. Yeah, here it's not like we don't. Here there are bounds for maximum achievable pre-distance, but we haven't discussed. In fact, you can view a convolutional code also as a block code of infinite length can also be viewed as a convolution with the time varying code.
Infinite length means we should achieve capacity.
No, infinite having a code word of length infinity doesn't mean we achieve capacity. See, convolutional codes performance is far from capacity. Okay, they don't achieve capacity. They have good coding gain, but there are limits to it because you can't increase D free indefinitely. At some point, it will saturate. There are bounds on D free. You cannot keep on increasing. So increasing D free will only give you some coding gain, but they won't achieve capacity. Turbo codes do something quite remarkable that we'll talk about. And by turbo codes, the code words are offered by the turbo codes are more like random code words. Okay, they are more random, and they are very long. Turbo codes achieve capacity when they are infinitely long. And basically, what they do is they concatenate two codes. So there's one code, and they put an interleaver that randomizes the sequence, and they put another code, and what is produced is essentially an instance of a random code word, and you transmit it, and you use this. Since you can't do maximum likelihood decoding for this system, you do iterative decoding. Right? You decode one code, followed de-interleave, decode, and then they condition, and then they try to achieve maximum. So sort of it connects to random coding argument. So LDPC also does something that what is that matrix? The parity matrix is almost like a random matrix in LDPC, and it's very large in size. Okay, so that's why they achieve capacity here. I'll discuss right they resemble random code words. They have more randomness in the code. These are, you can see, very deterministic. You have all zero code word, and then there is a fixed code word with the fixed minimum distance. You have the CDs from the previous lectures?